We spend a lot of time thinking about what is coming next, but what if the biggest mysteries lie not in the future, but in the echoes of what has already happened? Consider the light we see from a distant star. That light isn't arriving right now. It left its source, perhaps thousands of years ago. We are literally looking into the past, watching events unfold long after they concluded. This basic reality of light travel forces us to confront a complex question. If we are constantly observing the universe's history, does that history still exist, somehow stored in the fabric of space and time? We're not talking about memory or artifacts left on Earth. We're asking if the very events of the past are still present, just out of reach. We will explore how fundamental physics frames the concept of time and how distance equals delay in the cosmos, turning every telescope into a subtle time machine. If this kind of slow, deliberate exploration of the universe's deeper questions appeals to you, a gentle like and subscribe really helps us connect with others who share that curiosity. Settle in, and let's turn our attention to the light of yesterday. Time isn't just a reading on a watch. Before there were devices to track it, time was known by the processes happening within us and around us. It starts with the simple, steady movement of the breath, the shift of light as a day concludes, and the gradual, almost unnoticed growth of a child. We recognize time not as a set of numbers, but as change. Time is the label we give to the universal truth that nothing is perfectly still or exactly the same from one instant to the next. Imagine standing by a river and dipping your hand into the flowing water. The immediate coldness and the push of the current are real and present in that moment. But lift your hand and try again, and the river is already different. The water that touched you is gone, carried downstream. This observation that you cannot interact with the same exact moment twice because everything flows is central to how we understand reality. Despite this constant current, humans have always tried to capture time, building clocks to mark its passage and calendars to organize its flow. Yet, beneath these systems lies a more fundamental movement, a current that runs through everything. Your body keeps this time even without external aids. Inside you, life is measured by the dividing of cells and the rhythmic folding and unfolding of proteins. The heart maintains a steady, vital beat. Lungs automatically expand and contract in a rhythm so reliable, we often take its miracle for granted. Even when you are completely still, movement is happening inside billions of small, synchronized acts unfolding continuously. This is biological time, a form of time that needs no clock on the wall to be real. You feel its passage in the quiet settling of your body as you relax, in the gentle shift toward tiredness, and in the movement from tension to rest. Outside, the world operates on its own enormous clock. The earth turns, the moon dictates the tides, and flowers open and close. Change is constant, slow, quiet, and absolutely certain. This leads to the fundamental question: what is time? Is it a physical object, a location, or simply a process? We cannot hold it or store it. Some scientists suggest time is our unique way of making sense of change. Others argue it is a primary feature of the universe itself, intrinsically linked to space. In physics, time is defined as a dimension, much like height, width, or depth. It is a direction we are constantly moving through. We cannot stop, reverse, or skip ahead. If time is only change, we must ask why its flow feels so steady and locked in one direction. Why is it impossible to return to yesterday? This is a core mystery that physics continues to explore. While stories often treat time as a straight road, perhaps it behaves more like a spiral. Memory frequently acts this way. A certain smell, a piece of music, or a familiar shadow can make the past feel immediately present. Think of a vivid childhood memory, perhaps a bright birthday candle. Where is that shining moment now? It is not truly gone. It is stored inside you, shaping the person you are today. This suggests that time doesn't just move forward, it also builds you, layer upon layer, like sediment settling in a riverbed. You are not simply in time, time is in you. Language itself attempts to capture this elusive concept, saying that time passes as though it were walking, or that it flies as if it had wings. But these are only comparisons. You do not wait for time to pass. You are the one moving through it, gliding like a swimmer or drifting like a boat. This constant motion makes the central question unavoidable. If everything keeps moving, where does the past go? Where is the version of you from 5 or 10 years ago? Does that past vanish completely? Or is it hidden just out of sight, beyond the next bend in the river? Even if you do not actively notice it, every cell in your body is quietly keeping time. This internal timekeeping does not involve chimes, spinning hands, or digital displays, yet it is precise, ancient, and absolutely essential for life. Tonight, we drift inward, moving from the wide current of time we just discussed to the narrow, intricate canals of your own biology. The primary clocks in your body are made of molecules. They don't report the hour, they are the hour, keeping time by changing their shape, triggering chemical chain reactions, and guiding when the body should be alert and when it should rest. This mechanism is called your circadian rhythm, derived from Latin words that mean around a day. It is a 24-hour cycle deeply embedded within your cells. Even if you were completely isolated from external light, clocks, or calendars, your body would still track this rhythm. A tiny cluster of neurons deep inside the brain acts as the quiet conductor of this cellular timekeeping symphony. Beneath this conductor, cells throughout your body join in, using proteins as their molecular clock parts. These proteins are involved in a cyclical process. They build up, reach a peak concentration, then break down, only to start building up again. This repeating loop, similar to a pendulum, controls far more than just when you feel tired. This molecular rhythm guides your sleep cycles, your appetite, the regulation of your body temperature, the activity of your immune system, and even how quickly your liver processes sugar. You can think of these as internal tides, small cellular waves that rise and fall, not in response to the moon, but in response to the Sunday. Your body knows the difference between day and night by listening to light. When sunlight hits your eyes in the morning, specialized nerves send a signal from the retina to the conductor in your brain. That signal transmits the message, "It is morning, wake up, cells, begin the cycle again." Light effectively resets your inner clock every day. Conversely, when the sun disappears, your brain releases a chemical called melatonin, which acts as a gentle signal for rest. While you might feel the immediate effects like yawning, the underlying chemical messengers are diligently at work. Even individual organs operate on their own schedule. Your stomach prepares for digestion in advance of mealtime by releasing necessary enzymes. Your heart beats more quietly and slowly at night. Your muscles repair and rebuild themselves most efficiently while you sleep. Every single part of you follows a distinct rhythm, all harmonizing together. Problems arise when this rhythm breaks. Jet lag is not merely fatigue. It is a fundamental mismatch where your outside environment has shifted, but your inner clocks remain set to the time zone you left behind. Similarly, exposure to the bright, blue, and persistent light from electronic screens can confuse this sensitive system, whispering to your cells to stay awake when they are ready for rest. Still, your body is remarkably resilient, capable of adjusting and finding the rhythm again. The circadian clock is an ancient system, refined over billions of years. Even single-celled organisms, such as cyanobacteria in the ocean, respond to the 24-hour cycle of light and dark, proving this rhythm predates human existence by eons. You are not just living in time, you are fundamentally built to keep it. This internal rhythm continues even when you are asleep. Sleep is not simply the absence of activity. It is a vital, different kind of work. As you dream, your brain strengthens memories, sorts through emotions, and prunes unused connections. Your blood pressure drops, breathing deepens, and your body focuses on healing. The clocks keep ticking even as your conscious mind releases control. This rhythm extends beyond simple biology. We feel its pulse in the pacing of relationships, the unfolding of emotions, and the natural tempo of conversation and music. We are rhythmic beings within a rhythmic world. Sometimes, when people walk together, their steps naturally sync up. When a crowd is deeply engaged, their heartbeats can subtly align. There is a certain beauty in this hidden clockwork of human connection. As you continue to listen and drift, know that your patient body is keeping perfect time. It might be silent, but in that soft, internal ticking, there is an echo of where the river of time truly began. Before sleep completely takes hold, a new question emerges. If our bodies rely on cellular cycles to keep time, how does the mind handle it? Where does the feeling and shape of the past reside? Memory is not stored in a single, accessible location, like a labeled drawer or a film reel. You can simply rewind and play. Instead, it is far more fluid. Think of it as stepping into a calm body of water where the surface ripples, causing images to shift and rearrange. You do not remember using one specific brain region, but through many scattered centers, each holding different components of an event: the particular sound, the scent in the air, or the specific emotional reaction you felt. Whenever you remember something, your mind is not just retrieving the past, it is actively rebuilding it. It is like an artist reapplying old colors onto a fresh canvas. This process starts in the hippocampus, a small structure in the shape of a seahorse, tucked deep inside the brain. Here, various elements of an experience, a location, a person, and an emotional context are initially woven together, like threads starting a tapestry. This initial binding is not permanent, but it is enough to form the basic pattern. Later, the memory moves. It is distributed across the cortex to specialized areas, the visual processing parts, the centers for sound, and the emotional core of the brain. Each piece is stored separately, like scattered stars, which your mind must reassemble into a recognizable constellation later. This explains why memories are never perfectly still images. They subtly shimmer and change with every recall. They blend with other moments, borrow details, and gently bend. The act of remembering is not passive, it is creative, and every time you access a memory, you are also gently reshaping the memory itself. Consider a childhood story you have told repeatedly, a slightly lopsided birthday cake, or a summer that seemed to stretch out forever. Is that moment exactly as it originally happened, or has it been subtly colored by all the times you have recounted it, filed it away, and then pulled it back out? This is the paradox of memory. It is both a true anchor to the past and a slightly tinted, personalized version of it. But why does the brain operate this way? Memory is not intended to be a perfect, exhaustive record. Its primary purpose is to help you successfully navigate the future. The events you remember most clearly, a past danger, a significant joy, or a critical lesson, are the ones most useful for guiding your actions moving forward. The small, neutral, or unneeded details quietly fade into the background. This fading is a form of efficient adaptation and survival. The brain conserves energy by carefully curating and sculpting the information it keeps. Even forgetting is a designed function. You forget not because your brain is failing, but because it is making space and pruning old information to keep the system healthy. Yet, some memories resist fading. They suddenly surface without conscious effort, perhaps triggered by the smell of rain on warm pavement, the sound of a particular musical note, or the angle of the late afternoon sun. These are called involuntary memories. Your brain is constantly making quiet pairings, linking moments to meaning. A certain taste becomes tied to comfort. A specific location might become a map of an old grief. A laugh echoes the presence of someone missed. This emotional tagging, linking a memory to a strong feeling, is what gives the past its enduring power. You most vividly remember not just what happened, but how it felt. The mind is also remarkably imaginative. Sometimes, you may even remember events that never actually occurred. This happens because memory is not always literal. Two similar events might merge, or a story told to you over time might feel like something you personally experienced. Your brain fills in missing information, not to deceive you, but to create a cohesive whole. This is not a failure. It is the mind's way of making meaning. Even a false memory can hold an emotional truth, representing a real feeling, even if the surrounding scene is inaccurate. Furthermore, memory is used for more than just looking backward. It is essential for looking forward. You borrow from the past to imagine, plan, and dream up the future. The same neural pathways that activate when you recall a past event also fire up when you imagine a similar event yet to come. In this sense, memory allows a form of time travel in both directions. When you dream, these threads often weave together in surreal, non-linear ways. Memories drift into scenes that have no waking reality, and the strict rules of time soften. It is easy to think of memory as fragile, which it is, but it is also immensely powerful. It provides your continuous story and your sense of self. Without it, you would only be a series of isolated now moments. With it, you become a timeline, a complete narrative. Despite its softness and imperfections, your mind performs a truly miraculous task, holding your continuous self together across years, changes, and countless moments you have nearly forgotten. Now, let us move beyond the mind and float outward into the vastness of space. If our memories are personal echoes, does the universe itself possess a form of memory? Are there traces, subtle ripples, or scars among the stars that tell the story of where everything began. As we drift past the quiet blue curve of the Earth's atmosphere, we enter the immense void where the universe is constantly remembering. Everywhere you look, you find reminders of what came before. Nebulae are glowing with the remnants of stars that have long since died. Galaxies are tangled in motions caused by ancient collisions. Light is arriving from corners of the cosmos so distant that its journey began long before any humans walked the planet. Out here, the concept of new is rare. Everything you observe is essentially an echo, with light acting as a form of time travel. The farther you look into the distance, the farther back in time you are truly seeing. This is one of the profound facts of the cosmos. Looking across distance is the same as looking across time. For example, when you look at the Andromeda galaxy, you are not seeing it as it exists today, but as it was approximately 2.5 million years ago. This is because that is the amount of time required for its light to travel to your eye. When astronomers use large telescopes, they are fundamentally peering into history. They are observing a universe that was, not necessarily one that is in this current moment. The oldest, deepest echo in the cosmos comes not from stars or planets, but from something much quieter and colder. It is called the Cosmic Microwave Background, CMB. This technical name describes a remarkable physical reality, the faint afterglow of the Big Bang. It is a soft light that completely fills the universe, having been stretched and cooled over billions of years. Though invisible to the naked eye, it is always there, the universe's baby picture, captured when the cosmos was only about 300,000 years old, still warm and still expanding. This background light is detectable everywhere and in every direction. When scientists map it, they discover it is not perfectly uniform. There are extremely faint ripples, like temperature fingerprints, showing tiny irregularities. These tiny differences were the seeds from which everything visible eventually grew. From these early variations, the force of gravity was able to gather matter together, eventually creating the structures we see today: galaxies, stars, planets, and even ourselves. In this sense, the universe holds memory not just in light, but in structure. A star retains the memory of the immense gas cloud that condensed to form it. A black hole silently remembers all the mass it has consumed. Even the actual shape of space may hold a record of past events. These are not memories like human recollections. There are no images, language, or feelings involved, but they are structural, mathematical records etched into the very fabric of space and time. Some physicists propose that information can never be completely lost, not even when swallowed by a black hole. They suggest that every interaction, every particle, leaves a record or a trace written into the fundamental patterns of reality. If this hypothesis holds true, then nothing is truly forgotten, even in the deepest, most remote corners of the cosmos. The past does not vanish. It leaves an imprint, an echo, shaping everything that follows. Yet, these echoes slowly fade. The universe continues to expand, stretch, and cool. The intense, early heat of creation now registers only a few degrees above absolute zero, which is also known as 0 Kelvin, or approximately negative 459.6 to 7 degrees Fahrenheit. The cosmic signals grow fainter, and the space between galaxies grows wider. But even in this gradual fading, there is a quiet memory, a persistence that confirms, I existed. I was part of the beginning. Therefore, We are constantly surrounded by history, not in books, but in fundamental particles called photons, and not in stories, but in starlight. Consider this final thought. The atoms that make up your body, the calcium in your bones, and the iron in your blood were originally forged in stars, ancient ones that lived and died long before you were born. You are literally made of stardust. This is not poetic exaggeration. It is a statement of chemistry. You are not just in the universe is literally in you. Perhaps memory is not a burden we carry alone. Perhaps we are simply part of a system that remembers through us. Now, allow that idea to settle into stillness. In the next chapter, we will briefly leave the distant stars behind and return to Earth to examine the strange and beautiful ways that time bends right here in your own world. We often perceive time as a simple, constant, steady beat, much like the regular rhythm of a celestial metronome. This view was championed by thinkers like Isaac Newton, who envisioned time as a universal, fixed rhythm, ticking identically for everyone, everywhere. However, this established understanding was fundamentally altered by Albert Einstein, whose ideas demonstrated that time is not rigid. It can stretch, flow differently in various locations, and ultimately, it bends. Einstein's theory of relativity reveals that time is not universal. Its flow depends heavily on two factors, gravity and speed. Instead of thinking of time as a straight line, imagine it as a flexible, soft, invisible fabric known as space-time that stretches across the entire universe. Wherever there is significant mass, a planet, a star, or even your own body, this fabric dips, and this dipping is what we experience as gravity. Critically, where space-time dips, time itself slows down. This concept is not theoretical speculation. It is an established, measured, and tested fact. For instance, if you take two perfectly synchronized atomic clocks, placing one at sea level and the other atop a tall mountain, they will eventually fall out of alignment. The clock on the mountain, being slightly farther from Earth's gravitational pull, will tick a minute fraction faster than the clock at sea level. While imperceptible to human senses, this phenomenon is critical for modern technology. Global Positioning System, GPS, satellites must constantly correct their internal clocks for this time difference every single day. Without accounting for this gravitational time dilation, the location displayed on your phone's map could drift off course by several miles. If you are lying still and someone else is traveling high above you in an airplane, their clock is ticking slightly faster than yours because they are farther from the planet's gravitational center. Their body is aging a minuscule amount faster over time. If that person were to travel much faster, approaching the speed of light approximately 186,000 miles per second, or nearly 300,000 kilometers per second, their time would slow even more dramatically. To them, time would pass normally, but to an observer on Earth, they would appear to be moving in slow motion. This effect, known as time dilation, is the gentle warping of time caused by velocity and gravity. Consider a spacecraft that leaves Earth and travels near light speed. To the crew, only a few years may pass. However, when they return, decades may have passed on Earth. This is a core component built into the mathematics of the universe. Astronauts aboard the International Space Station, who are moving rapidly and are slightly farther from Earth's gravity, truly experience time a few milliseconds slower for every extended mission. They are technically returning to Earth slightly younger than they would have been otherwise. These small differences confirm that time is not a fixed constant. It responds directly to motion and gravity. This bending is not confined to clocks. It shapes the very structure of the cosmos. Einstein's greatest work, the general theory of relativity, established that space and time are fundamentally inseparable, forming the single entity known as space-time. Massive objects, stars, planets, and black holes warp this fabric like heavy stones placed on a trampoline. Light traveling past these objects does not move in a straight line. It follows the curve of the bent space-time. Gravity does not pull in the Newtonian sense. It bends space, and when space bends, time must also bend. While your mind experiences time subjectively, an hour can feel like a fleeting moment or a stretched eternity depending on your mood. Einstein's discovery concerns the fundamental physical structure beneath that feeling. He showed that time is not a ruler. It is a river whose flow is controlled by the presence of mass and gravity. Time is not floating past you. You are moving forward through it, always. Even as its speed subtly adjusts around the world's gravity, you are part of this cosmic dance. Now, let us settle into the gentle pull of the force that grounds you, gravity. Gravity is the constant, quiet force that keeps your feet on the floor, holds the oceans in place, and guides the planets in their orbits. But its deeper function is to subtly slow the flow of time. The core principle is simple but profound. The stronger the gravity, the slower time flows. This is not a metaphor. It is fundamental physics. Mass bends space, and that curved space dictates how time proceeds. To visualize this, imagine two identical, highly precise atomic clocks, one placed deep in a valley where gravity is slightly stronger, and the other placed high on a mountain where gravity is slightly weaker. Over time, the clock on the mountain will tick marginally faster than the clock in the valley. This is gravitational time dilation in action. The deeper you are within a gravitational field, such as the surface of a planet, the slower your time flows. This effect is why GPS satellites, which orbit thousands of miles above the Earth's surface, must be engineered to account for time running faster where they are. If these calculations were omitted, your navigational map would inaccurately drift by many meters or even kilometers every day. The people who built these systems know this well, and continuous corrections are made to keep the clocks of the ground and the clocks in the sky synchronized. Time, you see, is truly local. Its flow is specific to where you are standing. Now, consider objects with extreme gravity. Think of a neutron star, the super-dense, collapsed core of a massive star, compressed into a sphere no larger than a city. A small amount of this material, say the size of a single sugar cube, would weigh as much as all the ships in the world. Near such an object, gravity is immense, and time slows dramatically. For an observer orbiting close to its surface, a few moments could pass, while many years pass for someone observing from a safe distance. Even more extreme is the black hole, where gravity is so intense that nothing, not even light, can escape. Near its boundary, known as the event horizon, time slows almost to a complete stop. If you watched an object fall toward this edge, it would appear to you to slow down, seemingly freezing and hovering forever just before crossing the horizon. Though the descent would feel swift to the object itself, to the external observer, it is a slow-motion, vanishing act. It is a humbling realization that time The most reliable rhythm in your life can be so subtly stretched by gravity. Even your own heartbeat is fractionally slower because you are experiencing a slightly deeper gravitational field than someone just a few hundred feet above you. This difference is small, gentle, and utterly harmless, but it serves as a profound reminder that time is not a fixed construct. It is a soft, pliable fabric shaped by the mass and depth of the world around you. Some have wondered if this effect could be utilized to extend human lifespan by living in a powerful gravitational field, allowing one's time to flow slower relative to the rest of the universe. While this works in theory, the locations where gravity is strongest, such as collapsed stars or deep voids, are far too hostile for life. But perhaps we already participate in this slow tide. Every time you rest, as you are now, you submit your body to gravity. You let go, allowing yourself to be pulled gently downward. In this stillness, while time may not slow in a measurable, physical way, it feels different. Moments stretch, thoughts drift, and a minute can feel like a vast ocean of awareness. This moment of stillness, grounded by gravity, is the stillness that allows you to feel time in its simplest form, not as a number, but as a presence. The universe, contrary to the constant rush of daily life, tells us that time slows down where things are deep, still, and heavy. Slowness in this cosmic context is not a flaw, it is a truth. Gravity is not just a force pulling you down. It is a gentle invitation to be present, to be grounded, and to move slowly through the beautiful, curved flow of time. Now, let us look upward, past the ceiling and the clouds, and contemplate the light that has traveled vast distances across the cosmos, carrying messages from the past. We must ask, what does it truly mean to see something that may no longer exist? And how far back can a single beam of starlight truly carry us? Light is the ultimate speedster of the universe, moving at nearly 186,000 miles per second. That is fast enough to circle the Earth approximately 7 times in the span of a single heartbeat. But the cosmos is incredibly vast, and even at this blazing speed, light requires time to travel between objects. When you look at the moon, you are seeing the light that left its surface approximately 1.3 seconds ago. When you look at the sun, you are seeing the light that departed about 8 minutes prior. When you gaze at the stars, you are not seeing them as they are now. You are seeing them as they were years, perhaps even thousands of years ago. In this way, light functions as a message, a letter from the past, arriving long after it was initially sent. Every single photon, a particle of light, is a tiny messenger, silently traveling across the blackness of space. It bypasses planets, glides through the dark void, slips through the atmosphere, and lands softly in your eye. You do not feel or notice its arrival, but when it lands, it tells you the story of a star, of a specific time, and of a place that might have already ceased to exist. This is the strange reality of space. Seeing is not believing the present. Seeing is inherently remembering the past. The farther you look away from Earth, the farther back in time you are looking. A star located 100 light-years away is already a century behind you. The light you see tonight left that star before you were born, before much of the modern world even existed. Yet, that light shines brightly and clearly, full of the ancient wonder of what once was. Even if a distant star has ceased to exist, its light continues its long journey, carrying the image of that star across space like a visual message from a previous century. This light is not merely a beautiful sight. It is rich with information. Astronomers examine it like reading a detailed letter, using tools to break the light into a spectrum, a rainbow of finely detailed threads. From these patterns, they can precisely determine the star's chemical composition, its speed, and its exact distance, all contained within the simple beam of light. Each photon carries a unique, complex fingerprint of quiet data, allowing science to see deep into history, where the human eye only perceives brightness. Even deeper in the cosmos, there is light that has traveled not hundreds or thousands, but billions of years. Advanced telescopes, like the Hubble and the James Webb Space Telescope, peer incredibly far into space, which is equivalent to looking back in time. These instruments capture the glow of galaxies as they were first forming when the universe was only a fraction of its current age. They record the flickering of stars that lived and died before our own planet Earth had even solidified. In these most distant, faintest specks of light, we are seeing not just what was, but the fundamental origins of how our existence came to be. The vast darkness between stars is also not truly empty. It holds the faintest thermal hum, the cooled remnant of the Big Bang, the cosmic microwave background we discussed earlier. This, too, is a form of light, stretched and aged until it no longer registers as brightness, but as a subtle temperature above absolute zero. It is the last whisper of warmth left over from the intense energy of creation. You are constantly surrounded by this ancient light. Even during the deepest night, photons from long ago drift past you. Some might brush your skin, while others pass through you completely unnoticed. You are never isolated from the past. It flows through you constantly and quietly. Closer to home, light still carries temporal meaning. The golden shade of late afternoon, the soft blue wash of dawn, the gentle flicker of candlelight, each is light shaped by both time and place, colored by the sun's angle, the earth's curve, and the filtering of air and clouds. Even when you close your eyes, these images linger, not because the light is still present, but because your mind is echoing those moments. You might recall a starlit night, a quiet hillside, and the feeling of vast, timeless presence gazing back at you. Now you know that in that moment, you were truly looking across time. Every night sky is, in essence, a museum of ancient light, a vast gallery of photons still traveling home. As you drift now, let yourself float among these beams of light that have traveled so far. Consider this thought. If all we see is the past, then the present moment you are in right now is also on its way to someone, somewhere. You, in this very second, are becoming light, traveling into someone else's future. Let us now anchor ourselves in the sensation of now, this flicker of presence that exists between the seconds that have just passed and the seconds that are approaching. It feels fixed, like being anchored to a solid point in time. But science suggests that the now, the word we use for this very second, is not a fixed point at all. It is more like a blur, a gentle overlap between what has just concluded and what is just about to commence. By the time your brain processes and registers an event, even a tiny sound or a flash of light, that event has already moved into the past. You are always slightly behind the true moment, constantly interpreting, assembling, and making educated guesses. Your brain is not showing you the world exactly as it is. It is showing you a version of the world it has already finished building. To create the seamless flow of life, your mind acts like a weaver, stitching time together, It collects tiny delays from your senses. Your eyes and ears receive information at slightly different speeds and creates a smooth, continuous illusion. It eliminates inconsistencies, predicts what will happen next before it occurs, and fills in gaps you never consciously notice. This entire process takes time, milliseconds or microseconds, but it means that what you perceive as now has already elapsed. Neuroscience refers to this as the specious present. It is not a single point in time, but a short duration, typically lasting a few seconds. Within this window, your brain gathers enough information to maintain the feeling that events are continuous and connected. This is why you hear the complete melody of a song, not just a series of disconnected notes, and why you perceive fluid motion, not a sequence of still images. Your now is not a momentary instant. It is a short, rhythmic breath of time, just long enough to keep the narrative smooth. This illusion is not a fault. It is a critical feature. Without it, life would feel disjointed, fragmented, and incomplete. Your brain smooths out the world, arranging it into a calm, continuous story. And that story is what gives the present moment its meaning. Think again of the river. The water currently touching your skin is already moving downstream, yet to you, it feels immediate. The moment you consciously notice it, it is gone, but it leaves an impression, a memory in its wake. This is how your mind works. Each moment is flowing away, but its shape lingers gently in your awareness. Not all living things experience now in the same way. For some animals, time seems to flow faster because their brains can process more visual frames per second. To a hummingbird, your movements might appear incredibly slow, while to you, the bird is a rapid blur. Research suggests that different species have different lengths for their specious present, meaning each creature lives in a slightly different tempo of now. Even among humans, our perception of time shifts dramatically. When you are anxious, moments seem to drag. When you are deeply engaged, hours vanish. Time is demonstrably flexible in both your body and your mind. So, what is the present truly? It is not a single clock tick or a specific coordinate on the map of time. It is a fundamental sensation, a conscious state of awareness built from a layering of memory, expectation, and emotion. As the physicist Carlo Rovelli suggests, the concept of now is linked to the way our consciousness collapses the mathematical illusion of time. In the purely mechanical equations of physics, the past and future are often interchangeable. Yet in our human experience, time feels like an unstoppable arrow, and now is the tip of that arrow. It is perfectly fine to embrace and rest in the present, even with this scientific understanding. Even if it is a wave rather than a pinpoint dot, it is your home. It is where your breath happens, where memory is formed, and where imagination begins. The illusion of now is not a trick. It is the fundamental space of your experience. You are already a natural time traveler. Without any effort or machine, you move forward, 1 second at a time. You change, you age, you remember. Since birth, you have been effortlessly riding the current of time. But the question remains, could we ever reverse this flow? Could the future and the past ever meet again? In the language of physics, the idea of time travel is not mathematically impossible, though it is highly speculative. We begin not with fictional stories, But with the concept of space-time, the single, soft, invisible fabric that combines space and time, we have established that gravity bends this fabric, warping time near massive objects. But what if space-time were to bend not just gently, but so intensely that it curled back upon itself, forming a loop? Within general relativity, Einstein's fundamental theory, certain solutions to the equations hint at this possibility. These are called closed time-like curves. They represent paths through space-time that could, in theory, bring an object back to the exact place and time where it started. The idea of a loop in time, a circle where yesterday meets today, is an exotic mathematical possibility stemming from the same laws that describe gravity and black holes. However, a mathematical possibility does not guarantee a natural one. Many physicists believe these loops would be inherently unstable. The immense energy required to create one would likely cause it to collapse, or the slightest disturbance would tear it apart before any return could be achieved. Yet, the possibility remains, faint as a star, barely visible in the dawn sky. There are other, smaller whispers from the realm of quantum physics. At the level of fundamental particles, things behave in ways that defy everyday logic. Particles can exist in multiple states at once, and they can be entangled, meaning they are so deeply linked that changing one seems to instantly affect the other across vast distances. In certain theoretical models, particles appear to interact with their own past, briefly looping through probabilistic timelines and subtly touching events they have not yet reached. These are not full backward journeys, but they suggest that at the smallest scale, time might be far more flexible and textured than we generally assume. You may have heard of wormholes, often described as a shortcut through space-time, a tunnel connecting two distant points in space. Some versions of general relativity allow for their existence. Furthermore, some theories suggest that wormholes might link not just distant places, but different times. If one entrance of a wormhole were subjected to faster motion or deeper gravity than the other, it is theorized that a traveler emerging from the other end might arrive before they entered. But again, these remain speculative and fragile ideas. We have no confirmation that wormholes exist, nor do we know if they could ever be stable or safe to traverse. However, the universe does not forbid us from simply wondering, and perhaps this act of wondering is the closest we can come to experiencing time travel today. The concept of time travel, in its most profound form, forces us to confront essential questions, not just about physics, but about causality, free will, and paradox. If one were to travel back in time, the immediate question is whether it would be possible to change the past. What would happen if you prevented the very event that led to your own journey backward through time? These are known as causal paradoxes, knots in the fabric of time that logic struggles to untangle. Some scientific theories propose that the universe would inherently prevent such a paradox. They suggest that no matter what action a time traveler took, events would always unfold in a manner that preserves consistency. Other ideas lean toward time travel being possible only within strictly self-contained loops, a universe that allows for movement across time but prohibits fundamental contradictions. Yet, perhaps we do not need literal machines to achieve a form of time travel. We already travel through time in gentler, subjective ways, through deep memory, through vivid storytelling, or through the way a simple scent can instantly transport you back to a childhood kitchen. While these are not journeys governed by scientific equations, they are deeply real experiences. For the human mind, this may be enough. Still, It is acceptable, late at night, to consider the impossible, to imagine a discrete portal, a glowing opening hidden in the folds of space-time that could lead you back to a moment you had almost forgotten. Not to change it, but simply to witness it, to observe a past version of yourself, completely unaware of your nearby presence, just to remember more clearly. This contemplation leaves us not with certainty, but with awe. The laws of the universe, as far as we currently understand them, are vast and open enough to permit these profound questions. Not every question requires a definitive answer to hold meaning. Some questions, like the most distant stars, are beautiful simply because they exist and shine. Time moves forward, relentlessly forward. We age, we grow, we change, and events, once completed, become permanently fixed in the past. But why does this happen? Why is it that hot tea cools down but never reheats itself? Why do footprints appear in the sand and not the other way around? Tonight, we explore the source of this directionality, the fundamental reason why the past is fixed and the future remains open. In the deepest, most fundamental equations of physics, time holds no preference. The math works equally well whether time moves backward or forward. Yet our physical reality adheres to a strict direction. This one-way flow of time, the reason we remember yesterday, but not tomorrow, is called the arrow of time. This arrow consistently points from order to disorder, from structured patterns to greater randomness, from the improbable to the highly probable. The core concept shaping this arrow is entropy. Entropy is not exactly chaos. Rather, it is a scientific measure of how many possible arrangements a system can have. Think of a freshly organized desk. Every item is in its correct place, representing a state of low entropy. If the desk is completely shuffled, the number of possible disorganized arrangements skyrockets, representing high entropy. A whole, smooth egg held in your hand has low entropy. When you crack it, the resulting broken mess has far more ways to be messy and spread out than to revert to its perfect whole state. Entropy increases because there are simply statistically more ways for things to be disordered than for them to be perfectly ordered. Left to itself, any system will naturally tend toward the state with the highest probability disorder. Consider the effort it takes to build, clean, or organize something, and how quickly it can fall apart. This tendency is the soft, universal pull toward probability, toward even spreading. In thermodynamics, the study of heat and energy, this principle is known as the second law. Entropy in a closed system tends to increase. This is why heat flows from a hot object to a cold object, why ice melts, and why structures eventually crumble. It is the universe's natural unfolding. Yet, here is a beautiful truth. You, your organized body, and your conscious life exist because of entropy. You are not outside this process. You are a temporary, organized structure in a universe that is constantly spreading out. The energy that fuels your life from food, breath, and sunlight is part of this great cascade of change. You represent a brief pause in the river of increasing disorder, a pocket of order maintained by complexity and fueled by energy. Entropy is not destruction, it is change. When a log burns, it becomes ash, yes, but it simultaneously releases light and heat, warming a room and creating new energy patterns. The broken egg becomes breakfast, Disorder opens new paths and creates the necessary conditions for life and forward movement. Therefore, the arrow of time is not something to resist. It is the current we must simply ride. Why do we remember the past and not the future? Because our memories are built from traces, physical or chemical changes that reflect what has happened. A teacup cooling, fallen leaves on the ground, or a crease in a photograph. These traces only appear after an event has occurred. Because entropy always increases after an event, memory itself is an echo of entropy, a soft footprint left behind by the passing of time. It is theorized that the universe began in a state of incredibly low entropy, an extremely strange and improbable initial order. From that starting point, disorder had only one direction to go, up. And that movement birthed the arrow of time. You are still inside that initial cosmic breath. Every second, the universe becomes more entropic, but within this flow, there are temporary pockets of order, like the spiral of a galaxy or the cells of a living leaf. You are moving with the arrow, gently, naturally, and completely. So, tonight, let go of any need to rewind or return. There is no going back, but there is always becoming. Time does not just pass through your conscious mind. It passes through your physical body, softly, invisibly, but permanently. While your thoughts may forget and your memories may flicker, your body remembers in quieter, physical ways. In this chapter, we drift inward, not to your thoughts, but to the physical self that holds the entire history of your existence. Your body is not merely where time happens. It is where time leaves its permanent mark. Start with your skin. It stretches, heals, and sheds, recording both sunlight and scars. That small line on your knee from a fall years ago, or a freckle left by the summer sun. These are time made visible, moments recorded without conscious effort. Beneath the surface, cells constantly divide and die, rebuilding tissues over and over, but never perfectly. With each repair, tiny, lingering changes remain, like an ancient manuscript that has been repeatedly overwritten but never fully erased. Your bones also carry a record of time. They record not just your age, but your experience, a healed fracture, a subtle curve in the spine, or changes in density that occur as decades pass. Scientists can interpret bones like historical texts, inferring age, stress levels, and nutritional history from their structure. Your skeleton is a diary of every step you have taken, and though you may not feel it, your bones are alive, constantly renewing and reshaping. They do not forget. Even your teeth hold life stories. From the first ones that emerged to the molars that remain, tiny growth rings, similar to those found in trees, can reveal past growth patterns, shifts in nutrition, and illnesses long ago. Since enamel, once formed, never grows again, it permanently locks in the chemical history of your childhood, the water you drank, the minerals you absorbed, and the seasons you passed through. Your mouth holds literal fossils of your own life. Your muscles also, remember, not through cognitive thought, but through motion, reflex, and habit. The way your hands can tie a shoelace without conscious thought, the balance you instantly regain when riding a bicycle after years away, or the posture you naturally assume when tired. These are called muscle memories, stored not in the muscles themselves, but in the neural pathways of your brain, which are strengthened by repetition. Practice transforms effort into instinct. Time turns motion into permanent memory. Now, As you close your eyes and approach the doorway of sleep, the rules you know begin to soften. The sharp edges of time dissolve. Minutes lose their defined shape, and hours melt away. What emerges is a quieter, stranger realm, the world of dreams, where time is something else entirely. Your body rests, breath deepening, muscles relaxing, but your mind is active. During REM sleep, rapid eye movement, the parts of your brain that handle vision, emotion, and memory light up in vivid, unpredictable ways, like an orchestra preparing in the dark. This is the birthplace of dreams, and in dreams, time truly bends. You have likely felt this, a dream that seemed to last an entire afternoon, only to wake up moments later, or a dream where you leaped instantly across decades from childhood to the present day, or to a moment that never happened. Time in dreams is rarely linear. It is layered, fragmented, and woven from feelings rather than clocks. Your dreaming self does not check the time. It simply exists in whatever moment appears. While the exact purpose of dreaming is still being studied, many theories suggest that dreams serve to consolidate memory, to sort, file, and gently reframe the experiences, emotions, and fears of the waking day. The hippocampus, the memory keeper, seems to be active in the background, subtly replaying patterns and strengthening connections. Studies indicate that during dreams, your brain reactivates recent experiences, not as perfect repetitions, but as remixes, snippets stitched together, colored with emotion, and shaped by fragments of long-forgotten days. Because memory itself is not a straight line, neither are dreams. In a dream, time may loop. You might wake up only to find yourself dreaming again. You might speak to a person long gone, and it feels completely natural. You may revisit a childhood home that no longer exists in reality, its walls and details preserved more sharply in your mind than they ever were in life. Here, time does not anchor you. It moves freely with your imagination. The brain, during sleep, operates outside the established rules of the waking world, particularly concerning time. Some dreams execute a radical compression of time, creating the psychological experience of living an entire complex narrative, perhaps a whole day or even a lifetime within a few minutes of biological rest. Conversely, a single, fleeting event in a dream, such as a sharp glance or a solitary word, can be stretched into a vast, seemingly endless mental landscape. These temporal shifts are not random errors in brain function. They are precise reflections of how the mind prioritizes meaning, weighting emotional intensity and depth of processing over the consistent tick of an external clock. In this sleeping state, the brain measures time in terms of salience, how important or intense a feeling is, rather than in simple, sequential seconds. This is why a dream featuring a long-lost loved one, however brief, feels more significant than hours spent performing a mundane, continuous task in reality. A rare and fascinating example of the mind taking command of this subjective time is the state of lucid dreaming. In this state, a sliver of conscious awareness rises above the dream's narrative, allowing the dreamer to recognize and manipulate the environment. During lucidity, the dreamer can directly influence the flow of time. They can shape the surrounding world, command the narrative to slow down dramatically, or even attempt to move backward through the dream's recent events. In these moments, the dreamer is not merely a passive traveler through time, but its active author, holding the perception of time like malleable material. The the strict constraints of waking physics are lifted. Space does not need to be linear, and time does not need to be constant. The only necessary condition is that the experience must be felt internally. Despite this subjective freedom, the dream state is rigorously tethered to our biology. The timing, duration, and content of dreams are influenced by the circadian rhythm, the cyclical pattern of the different sleep stages, and the specific types of brainwaves being generated. The most vivid and temporally distorted dreams primarily occur during REM sleep, rapid eye movement, a stage characterized by brain activity similar to wakefulness. However, fragments of dreaming can emerge during other, deeper sleep stages, rising like deep-sea bubbles. Sleep is a complex, layered process, with each stage offering a unique version of time perception. When the mind emerges from sleep, the remnants of the dream can be anything from total oblivion to a single, haunting image or a lingering emotional residue. While some dreams vanish instantly, others are recurrent, repeating their narrative like old messages rediscovered years later. Regardless of conscious recall, the brain's processing work is complete. Studies indicate that sleep, particularly REM sleep, is vital for memory consolidation. The hippocampus, the seahorse-shaped region responsible for initial memory formation, works intensely during the night, subtly replaying and strengthening neural patterns related to recent experiences. However, these replays are not perfect copies. They are more akin to complex remixes, stitching together snippets of events, coloring them with residual emotion, and shaping them with unrelated fragments from older memories. Because memory itself is a process of reconstruction rather than simple retrieval, the resultant dreams are inherently non-linear. As we conclude this segment, having adhered to the linear discipline of clocks and the predictable flow of the day, allow time to surrender its tight grip. Let the concept of time spiral and sway, and enter a state where the past and the future are simply malleable settings. Following the ephemeral time of the mind, we now anchor ourselves to the profound, measurable stillness of the planet. This stillness is not an absence of activity, but a quiet, constant accumulation of history, time compressed, folded, and stored beneath our feet. The Earth acts as a vast, non-biological archive, recording its history not in dreams or words, but in geological strata, biological rings, chemical signatures, and frozen layers. One of the most accessible records is found in trees. As a tree grows each year, it produces a new ring of cells, a visual record of the environmental conditions. This ring is a precise response to sunlight, water, and air. Wide rings signify years of favorable climate, such as ample rain and warmth, while narrow rings indicate stress, such as drought or severe frost. The science of reading these rings is called dendrochronology. By analyzing the patterns of these rings across a forest, scientists can create a master chronology, revealing climatic events that occurred over thousands of years, including major drought cycles, the dimming effect of prehistoric volcanic eruptions, and even evidence of powerful ancient solar storms. A forest, therefore, serves as a silent, self-updating historical record, with each tree functioning as a historian etched in the concentric circles of wood, fiber, and time. The Earth's memory is also stored in rock layers. Over immense spans of time, millennia to millions of years, fine materials like wind-blown dust, volcanic ash, decomposed organic matter, and tiny mineral fragments settle, layer by layer. Through immense pressure and chemical processes, these layers solidify into rock, forming distinct strata of shale, limestone, or sandstone. The study of these layers is stratigraphy, which divides Earth's history into chapters defined by specific rock formations. Each layer possesses a unique color and texture, representing a different era of the planet's environment. Embedded within these strata are fossils, not only bones, but also the impressions of ancient leaves, microscopic pollen grains, and even the preserved footprints of creatures hardened in ancient mud. These fossils are precise timestamps, indicating when species evolved, when global sea levels rose and fell, and when major continental shifts occurred. Perhaps the most astonishing time capsule is found in the polar regions, ice core science. In glaciers and continental ice caps, snow falls and compacts year after year, trapping tiny, pristine samples of the ancient atmosphere. Scientists drill deep into this ice, retrieving cylinders that contain layers stretching back more than 800,000 years. The deeper the ice core, the older the trapped air and material. By analyzing the tiny air bubbles within the ice, researchers can measure atmospheric gas concentrations, including carbon dioxide and methane, providing a direct record of temperature fluctuations and the chemical composition of the air that existed long before the modern industrial age. Geological materials also hold deep chemical memories. Mountains hold the record of violent continental collisions, while the chemical composition of rocks can be used for radiometric dating, allowing scientists to calculate the absolute age of geological formations based on the slow, predictable decay of radioactive elements. The most ancient physical memory we have located is in tiny crystals of zircon. These remarkably resistant crystals, some measuring over 4 billion years old, were among the first materials to form on the Earth's cooling crust. Inside these grains, often smaller than a grain of sand, scientists have found chemical evidence that points to the earliest presence of water and the formation of the planet's first continents. The oceans also maintain an extensive, slow-moving archive. Sediments continuously drift and layer the seabed. Deep-sea corals grow in rings, and the chemical composition within their skeletal structures records shifts in ocean temperature and water chemistry. The cumulative, relentless force of ocean waves shapes coastal stone over centuries, turning coastlines into enduring records of erosion and geological stability. When we rest on the Earth, we are physically grounded on a composite story, a million overlapping tales told through texture, weight, and chemical form. Our own existence is inherently linked to this archive. The atoms in our bodies originated from the materials of this soil and ancient stardust. When we gaze upward, we perceive the stars as being fixed in their positions, a permanent backdrop against which our lives play out. We rely on familiar patterns like the Big Dipper or Orion's belt to feel anchored in time and space. However, this perception of stillness is a profound optical illusion. The stars are, in reality, engaged in a majestic, silent dance. But their motion is so vast that it takes centuries for human observers to detect the change. Every star visible in the night sky is moving rapidly, not just burning brightly, but physically traversing space at speeds that can reach tens of thousands of miles per hour. Each star follows its own unique, massive orbit around the gravitational center of the Milky Way galaxy. Yet, because the distances are so immense, any change in position appears incredibly gradual, like watching distant ships drift across an enormous, silent ocean. This measured, slow displacement of stars across the sky is called proper motion. Astronomers use specialized, highly sensitive instruments to measure this migration, charting the movement of stars against the backdrop of more distant, static galaxies. Over historical timescales, these small, constant motions accumulate. The constellations we recognize today, the shapes we draw by connecting the dots, are therefore temporary formations. They are geometric snapshots, shapes traced from our specific, current point of view on the edge of the galactic plane. If we were able to accelerate time to observe the movement, the familiar patterns would visibly stretch, distort, and dissolve. The fixed lines of Orion would unbuckle, and the Big Dipper's shape would flatten. The constellations are not eternal. They are merely the current arrangement in a continuously evolving stellar landscape. Furthermore, individual stars appear and disappear from our visible catalogue. Some stars, like the faint red dwarf Barnard's star, possess a remarkably high proper motion, meaning they are moving across our line of sight faster than most others. Conversely, other stars are moving directly toward us or away from us. A notable example is Gliese 710, which is currently projected to pass close to our solar system in approximately 1.3 million years. While it poses no threat to humanity today, its close approach may exert a powerful enough gravitational influence to perturb the Oort cloud, the distant, spherical cloud of icy bodies surrounding our solar system, potentially scattering comets inward like a silent cosmic snowstorm. The disappearance of stars also forms part of this temporal narrative. Events that ancient astronomers referred to as guest stars, bright, unexpected lights in the sky, were often the final, violent explosions of massive stars, known as supernovae. These are the magnificent, final acts of stellar collapse. The light from these stellar deaths, though instantaneous in cosmic terms, often takes years, decades, or even centuries to traverse the vast interstellar space before finally reaching Earth. Therefore, whether you are observing a star that is still burning or witnessing the faint light of a star that died millennia ago, you are fundamentally looking into the past. The light you perceive tonight embarked on its journey before recorded history began. The night sky is, in essence, a photograph taken from within a constantly moving time machine. You are not separate from the massive celestial dance we have discussed. You are inside it. The Earth rotates on its axis. The Earth orbits the Sunday. The Sun, in turn, orbits the gravitational center of the Milky Way galaxy at a speed of approximately 140 miles per second, or 230 kilometers per second. And the galaxy itself, along with our local cluster of galaxies, is flowing through the vast, expanding cosmos. Your single existence is a fraction of a moment in this colossal, slow choreography of stars, too subtle to feel directly, yet too vast to ignore. When you look up and focus on a distant star, you are effectively touching something that may no longer exist in the present. Some of the brightest stars you see have already exhausted their core fuel and ended their lives. Their light continues its relentless journey, flickering across interstellar distances to reach your eye, even though their nuclear fire has been extinguished. Does this make the light less real? No. It confirms that the past is still arriving, and that the energy of a star can survive its source, shining as a powerful echo. This continuous arrival of the past confirms that even your personal stillness is part of a much larger, constant rhythm. This cosmic movement leads us to a deeper, more fundamental question. Did time itself have a beginning? Was there a moment before time began? This question is inherently elusive. We are conditioned to think in terms of sequential beginnings, a story, a song, a life. But applying the concept of before to time itself causes the term to lose its meaning. For centuries, many believed the universe was static and eternal, stretching infinitely backward and forward without an origin. The major shift in the 20th century came with the development of the Big Bang theory. This theory describes not an explosion in space, but the rapid expansion of space itself, a sudden, singular moment from which all matter, energy, and, critically, space-time unfurled. If time commenced with the Big Bang, then asking what came before is akin to asking for the location that is north of the North Pole. The question sounds logical, but the concept of before is rooted in time, and if time itself began at that singular point, then before may not exist as a meaningful concept. Time may have emerged like light from darkness, or like a melody from silence. However, not all physicists subscribe to a single absolute beginning. Some theoretical models suggest that our universe might be one segment in a cyclic model, a vast process where the cosmos expands and then collapses, only to expand again in an endless oscillation. These models stretch time not into a straight line, but into perpetual loops. Other theories invoke quantum gravity, which explores physics at the most fundamental scales. Here, the fabric of space-time becomes chaotic, fraying into a foam where the clear distinction between past, present, and future dissolves entirely. At these scales, the rules of our predictable, macro world break down, and time loses its steady, measured rhythm. Some physicists now propose that time is not a fundamental property of the universe, but is emergent, something that developed later, like ripples forming on the surface of a pond. In this view, time is not the stage on which the universe plays out. It is an intrinsic part of the play. This suggests that even the most basic human feeling that time flows consistently forward might be a form of necessary illusion, a sensation generated by memory, change, and the constant increase of entropy. Time may not be real in the same way as matter or energy. It may be a descriptive tool used to narrate the sequence of events. The cosmic story began when the universe found sufficient order to track its own unfolding, when difference and change became possible. This leads to the lingering mysteries. Was the Big Bang the absolute first event, or just one note in a much longer, ongoing song? Does time flow forward uniformly throughout the entire cosmos? Could our universe be mirrored by another, where time flows in reverse? We do not possess the answers, but the questions themselves are a source of profound wonder. Every breath you take is part of this cosmic unfolding. Time may not be absolute, but it is real to you in this present moment. Following the vast scale of cosmic beginnings, we return to a process that is small but equally powerful: forgetting. Memory fades even as the body continues its constant renewal. We must explore the mechanism of forgetting, why the brain actively releases information, and how this process is integral to the movement of time through us. There is a profound sense of calm and natural forgetting, not the frustration of misplacing an object, but the slow, quiet fading of a memory's sharp edges, a soft blurring as a past moment drifts into the background. Forgetting, like remembering, is not a biological flaw. It is an active, essential part of how the mind processes and moves through time. The brain is not a comprehensive, unselective storage drive designed to hold every second of your existence. It is highly selective. It holds on to information deemed essential for future navigation and survival, while quietly releasing the rest. This process is highly sophisticated and is, in fact, an active biological design. Forgetfulness is not merely the absence of memory retrieval, it is an active process of pruning and reshaping the neural landscape. The brain employs distinct, measurable mechanisms to manage the process of forgetting. The first mechanism is passive fading, or decay. This occurs when specific neural pathways, the microscopic connections that encode a memory, are not repeatedly activated. Over time, these pathways diminish and grow dim due to disuse. Second, active overwriting, or interference, occurs when the input of new information disrupts the integrity of existing similar older memories, effectively replacing the old data. The third mechanism is active dismantling, a process where the brain intentionally regulates memory strength. This involves the release of specific chemical agents that weaken the synaptic connections holding a memory together. For instance, a protein identified as PP1 functions as a natural eraser, controlling the strength of these memory links. Maintaining an appropriate concentration of this chemical is critical for balance. Excessive amounts cause essential memories to fade rapidly, while insufficient amounts can lead to a mind overwhelmed by an excess of irrelevant detail. Through these processes, the mind actively clears space, facilitating continuous learning and adaptation. In cases of emotional or physical trauma, forgetting can be a self-protective mechanism. The memory is not entirely erased, but it may be sealed away, becoming a blurry shape in the distance rather than a disruptive presence. Conversely, the frustration of forgetting a common name is simply the brain prioritizing efficiency. There is a unique beauty in this rhythm. To forget is to grow. To forget is to shed. Children forget much of their earliest years because their developing minds are still creating the organizational tools necessary to hold complex chronological time. As we age, while we may forget mundane details, what we wore, what we said, the emotional trace, and the pattern of what something meant often remain. Memory becomes lighter, focused on meaning rather than perfect factual recall. The past cannot be carried in its entirety. What is forgotten falls away like petals or leaves. This is evolution. We are not simple storage containers, but a river of continuous change. This biological forgetting is mirrored throughout the physical self. Cells die and are replaced. Skin renews, blood cycles. You are never the exact person you were last year, neither in memory nor in physical matter. However, certain memories resist this process. Those linked to love, fear, survival, or profound learning. These are carved more deeply, reinforced by emotional intensity, and are essential for survival. Recent studies increasingly frame forgetting not as a deficit, but as an active tool for clarity. By shedding extraneous details, the brain can better grasp the larger, overarching pattern. Forgetting minor steps allows for adaptation, improvisation, and creativity. In this context, forgetting is not the opposite of remembering. It is the other side of the same coin, a cycle of encoding, retention, and necessary release. Time feels perfectly smooth to our consciousness, a gentle, uninterrupted flow from one soft moment to the next. However, if we could shrink down past the scale of our skin, cells, and atoms into the absolute tiniest scales of reality, time begins to exhibit radically different behaviors. We shrink now into the quantum world, where time may not be smooth and continuous, but rather grainy, built from tiny, discrete, trembling pieces. Here, the universe ticks not like a reliable metronome, but like a cloud of probabilities. In this quantum realm, particles are not fixed, solid objects. They are better described as waves of probability blurred, humming smudges of uncertainty. An electron does not exist in one fixed location. It hovers or flickers in and out of likelihood. In this strange environment, time does not adhere to neat lines. It appears to dance, interfere with itself, and certainly does not always tick at a uniform rhythm. In the physics of our everyday world, classical physics, time is treated as a uniform, unchanging, dependable backdrop. The laws of motion assume that time is an independent variable, moving steadily regardless of what happens within it. However, the fusion of quantum mechanics, the physics of the very small, and general relativity, the physics of the very large, like gravity and space-time, suggests a profound challenge to this smoothness. The theoretical framework of quantum gravity proposes a smallest possible unit of distance, known as the Planck length, approximately 10 to the power of -35 meters. If space is quantized, built from tiny, indivisible packets, it suggests that time, which is interwoven with space, may also be quantized. This hypothesized smallest unit of time is called the Planck time, approximately 10 to the power of -43 seconds. Below this level, the concept of time as a continuous flow breaks down. If this is true, time is not smooth like water. It is granular, like fine sand. Our perception of time as continuous is only because the grain size is unimaginably small. Furthermore, within quantum physics, the act of observation fundamentally affects a particle's state. When we try to measure something like a particle's location, the particle snaps from a state of probability into a definite reality. This raises the question of whether time itself is something that is measured or something that is created by the act of observation. The concept of the quantum clock also complicates our understanding. A clock works by counting events, the swing of a pendulum, the vibration of an atom. But what happens if the clock itself is subject to the bizarre rules of quantum mechanics? If a clock exists in a superposition, being in two states at once, then the very measurement of time becomes blurred. Some physicists suggest that in the quantum world, particles may not have fixed trajectories in time. Their movement might be better described by a probability distribution that includes a slight chance of looping back, even if only for an instant. This exploration into the quantum foam suggests that time is not fundamental, but rather an illusion that emerges from the statistical behavior of countless particles adhering to the second law of thermodynamics, entropy. Time is what happens when order breaks down into disorder. It is the statistical arrow we perceive as forward motion. At the ultimate small scale, the arrow of time vanishes, and everything is just probability. Time feels perfectly continuous to our everyday awareness, a smooth, gentle flow. However, if we could shrink our perception down past the scale of our skin, our cells, our molecules, and our atoms into the tiniest dimensions of reality, time begins to behave dramatically differently. We enter the quantum world, where time may not be smooth and continuous, but rather grainy, constructed from tiny, discrete, trembling packets. Here, the universe ticks not with the reliable swing of a pendulum, but with the subtle hum of probability. In this quantum realm, fundamental components are not fixed, solid objects. They are better described as waves of probability blurred, humming smudges of possibility. An electron doesn't occupy one location. It hovers or flickers in and out of likelihood. In this strange environment, time does not adhere to predictable, neat lines. It appears to dance, interfere with its own past, and certainly does not always tick at a uniform rhythm. In the physics of our observable world, classical physics, which governs planets and falling objects, time is treated as a fixed, unchanging, dependable backdrop. The laws of motion assume that time is a constant variable, moving steadily regardless of the events within it. However, the theoretical fusion of quantum mechanics, the physics of the very small, and general relativity, the physics of the very large, such as gravity and spacetime, suggests a profound challenge to this smoothness. The theoretical framework of quantum gravity proposes that there must be a smallest possible unit of distance, known as the Planck length, which is approximately 10 to the power of -35 meters. If space is built from tiny, indivisible packets, it follows that time, which is interwoven with space, may also be quantized, meaning it is made of tiny, fundamental units, like pixels that cannot be divided further. This hypothesized smallest unit of time is called the Planck time, which is approximately 10 to the power of -43 seconds. Below this duration, the very concept of time as a continuous flow breaks down. If this theory is correct, time is not continuous, like a river. It is granular, like extremely fine sand. Our perception of smooth continuity only holds because the grain size is unimaginably small. In this view, time is not a river, but a staircase so exquisitely fine that from a distance it appears perfectly smooth. These hypothetical quantum pulses are the rhythms that keep our most precise timekeepers. The most accurate clocks in the world are not built with mechanical gears or pendulums. They are constructed using atoms, specifically by measuring the energy jumps within elements like cesium or ytterbium. Inside these atoms, electrons transition between energy states, emitting a tiny pulse of light at a specific, highly stable frequency. That frequency is so reliable that it defines our fundamental unit of time. 1 second, by international definition, is the duration of 9,192,631,770 oscillations of radiation from a cesium atom. Each tick is a direct whisper of this quantum rhythm. These atomic clocks are so precise they would deviate by only 1 second over billions of years. Scientists are now developing even more accurate devices, such as those using optical lattices and ultra-cold atoms, which can measure time on a scale so fine they can detect how gravity slightly alters the flow of time across distances as small as 1 millimeter. These quantum clocks are not just measurement tools, they are precise windows into the underlying structure of time itself. Yet, in the quantum world, not every event follows a clear, sequential order. Some experimental evidence suggests that time might not always possess a defined sequence. Events A and B can occur in a state of superposition, where it is impossible to determine which happened first. It is an entanglement of events where there is no clear answer. Furthermore, some theoretical models of quantum gravity propose that time might not exist at all as a fundamental ingredient of reality. In these theories, time is not a background stage, but rather a side effect or a relationship that emerges only when systems become large enough to be observed. Time, in this context, is a consequence of perspective. Though your mind does not consciously perceive Planck time, and your breath doesn't tick like a cesium pulse, these tiny, fundamental rhythms continue beneath your perception. At the smallest scale, time is pulsed and grainy, but its effects ripple outward into life and memory. You are a wave that moves through multiple layers of time, some smooth, some granular, some incomprehensibly fast. Even in your stillness, a deeper ticking persists, carving the shape of your life one grain of time at a time. You are constructed from the quantum world, and its pulses carry you forward. Now, we zoom out to the massive, mysterious, and shadowed objects known as black holes, regions where gravity is so intense that time severely bends, matter collapses, and the concept of information conservation is fiercely debated. A black hole is not an empty void. It is a region of space where gravity is so overwhelming that nothing, not even light, can escape its pull. When a massive star depletes its nuclear fuel, its core violently collapses inward under its own immense weight. The core condenses into an infinitely dense point called a singularity, which is surrounded by a boundary known as the event horizon. Once matter crosses this horizon, the established rules of spacetime begin to blur and warp. To an observer positioned far outside the black hole, an object falling inward appears to slow down dramatically as it approaches the event horizon. Time stretches infinitely for the falling object from the observer's distant perspective. The object seems to freeze at the boundary, forever fading, but never quite crossing. However, from the perspective of the object itself, time continues normally, and it passes through the horizon in an instant. This dramatic difference in time's flow is a key paradox in the geometry of black holes. For decades, the standard belief among physicists was that anything falling into a black hole was simply gone. This included not just the matter itself, but its information, the precise details of its shape, temperature, and structure. This idea that information could be destroyed completely violated a cornerstone of quantum mechanics, which stipulates that information cannot be truly lost. It can only change form or spread out, but it must be conserved. This contradiction ignited what became known as the black hole information paradox. The influential physicist Stephen Hawking initially argued that information does indeed disappear. He proposed that black holes slowly evaporate over billions of years through a process called Hawking radiation, and when the black hole is entirely gone, the information it contained is gone, too. However, the consistency and precision of the laws of quantum physics led many scientists to strongly disagree with the notion of such fundamental forgetting. The question then evolved: if matter falls into a black hole, is it ever truly lost? Or does the universe possess methods of remembering we do not yet understand? Many contemporary scientists now theorize that the information is not lost, but stored, etched, or encoded onto the two-dimensional surface of the event horizon, not inside the singularity. This concept is the holographic principle. It suggests that the boundary of the black hole acts like a hologram, a two-dimensional pattern that fully encodes all the information about the three-dimensional reality contained within. This principle extends to the entire cosmos. Perhaps the fabric of all reality is woven with subtle patterns and ripples that never fully disappear. If this is true, every action, every energy flicker, every thought leaves behind a residual trace, an imprint that the universe carries forward. In this sense, black holes may not function as graves of matter, but as vast, dark archives where information is kept secured by gravity's immense lock. Just as ancient fossils reveal the story of long-gone creatures, these informational imprints might tell the story of collapsed stars and matter once vibrant with motion. This cosmic memory implies that you, too, are part of this indelible fabric. Your presence leaves a permanent mark. Even the smallest actions, a single breath, a quick step, a spoken word, have nudged the universe, however infinitesimally. Physics dictates that information, once created, cannot be unmade. You are not erased. You are remembered in ways the universe may carry forward long after your personal memories fade. Not all disappearance equates to loss. The past does not vanish. Sometimes it is preserved, whispering in the gentle bend of space and the dark silence that keeps watch. Even now, as you lie in stillness, time is moving through you. It is not rushing or harsh, but gently brushing across your cells. This process is called aging, not a single event, but a continuous rhythm and transformation woven into your fundamental biology. We approach this rhythm not to resist it, but to understand how time shapes us slowly and softly. Aging begins at the very moment of inception, from the first division of cells and the first beat of a tiny heart. However, aging is not merely a trajectory of decline. It is a complex process of growth, adaptation, and change, guided by time. You are not biologically identical to the person you were last year, last month, or even yesterday. You are a river, always flowing and never quite the same from one instant to the next. One of the quiet clocks of aging operates inside your cells, involving tiny structures called telomeres. Imagine them as the plastic tips on the ends of shoelaces. They protect your DNA from unraveling. Each time a cell divides to replicate itself, the telomeres become slightly shorter. Eventually, they shorten to a critical point where they can no longer protect the DNA. At this stage, the cell ceases to divide it effectively, retires, or undergoes controlled cell death. This shortening is one of the measurable biological markers of time's passage. However, aging represents a layering of experience that transcends simple mechanical wear. Your body continuously adapts. Bones grow stronger from stress before gradually softening with rest. Your skin matures and later thins. Your immune system is a conversation with time. It matures by learning and building a comprehensive library of pathogens encountered in the world before gradually becoming less reactive and more cautious later in life. This is not a mechanical breakdown. It is a long, continuous dialogue between time and your internal biological systems. Nature showcases many alternative approaches to time. For example, the hydra, a tiny freshwater animal, appears to exhibit no signs of cellular aging, continuously renewing its cells and achieving a state of potential biological immortality. Certain species of jellyfish possess the unique ability to revert back to an earlier life stage, effectively reversing their biological clock. Similarly, some mammals, like naked mole rats, demonstrate extraordinary longevity and resistance to common age-related declines. These examples confirm that nature employs multiple varied tunes when conducting the rhythm of time. Humanity, through history, has persistently sought methods to slow this rhythm, ranging from ancient myths to modern scientific exploration of senescence, the process where cells lose the ability to divide. We study specific molecules, measure cellular inflammation, and track the effects of oxidative stress. We engage in practices like controlled fasting, disciplined physical activity, and careful nutrition. Yet, despite these efforts, the fundamental biological rhythm continues. You are fundamentally involved in this colossal motion. The Earth rotates. The Earth orbits the Sunday. The Sun orbits the center of the galaxy. And the galaxy itself, part of a cluster, flows through the vast, constantly expanding cosmos. You are not separate from this celestial dance. You are inside it, a single, living moment, in a choreography of stars too slow for your body to feel, yet too magnificent to ignore. When you focus on a star and express a hope, you are reaching out to light that may no longer have an active source. Some of the starlight reaching you tonight originates from stellar cores that have already cooled and darkened. Does this fact diminish the light's reality? Absolutely not. It confirms that the past is still arriving and that beauty and information can endure beyond their original source. You are seeing pure echoes, and those echoes still possess the power to shine. While constellations shift, stars drift, and light bends, the cosmic patterns persist, ensuring that even your stillness is part of a much larger, continuous rhythm. This leads us to the ultimate profound question. Did time itself have a beginning? Was there a foundational moment before time even existed? This is a question that resists conventional linguistic frameworks. We are accustomed to sequential beginnings, but applying the term before to time fundamentally dissolves the question at the edge of the known universe. For a significant period, the prevailing scientific belief, championed by figures like Isaac Newton, was that the universe was eternal, stretching infinitely backward and forward. The 20th century introduced the theory of the Big Bang, not an explosion in space, but the rapid expansion of space itself, a sudden, singular breath from which all matter, energy, and, critically, space-time unfurled. If time commenced with the Big Bang, then what came before loses its meaning. Much like asking for the direction north of the North Pole, there may have been no before. Time may have simply emerged, like light from darkness. Yet, this certainty is challenged by alternate cosmological models. Some theories propose that our universe is one isolated bubble in a larger cosmic sea, suggesting that time extends backward into cyclic models, where the universe expands and collapses in endless oscillation. Others delve into quantum gravity, a realm where the fabric of space-time frays into a foam, and time loses its established meaning, operating not as a fundamental ingredient, but as an emergent phenomenon, a consequence of observation and statistical mechanics. In this view, time is not the fixed stage. It is an intrinsic part of the dynamic performance. This leads to the realization that the most basic sensation of time flowing forward may be an illusion, a sensation born from the memory of change and the constant, relentless increase of entropy. Time may not be a tangible thing, but a method used to narrate events. The cosmic story began when the universe developed sufficient order to track its own change when difference was born. Even now, mystery remains. Was the Big Bang the only beginning, or simply one note in a longer, infinite composition? Does time always move forward, or are there theoretical corners of the cosmos where it reverses? These questions may never be fully answered, but they serve to humble us and invite continuous wonder. Every moment, every breath you take is part of this unfolding. Time may not be solid, but it is deeply personal and real to you. Following the grand scale of cosmic time, we return to the subtle, essential process of forgetting. Memory fades, even as the body persists. We explore the mechanism of forgetting, why the brain actively lets go, and how this process is vital to the continuous movement of time through us. There is a natural tranquility in forgetting, not the anxious loss of misplacing something, but the slow, quiet fading of a memory's sharp edges as it drifts into the background. Forgetting, like remembering, is not a failure. It is an active, essential process that allows the mind to move through time effectively. Your brain is not a static recording device. It is a dynamic, selective system. It retains information necessary for survival and future navigation, while actively releasing the rest. Forgetfulness is not merely the absence of memory retrieval. It is a biological pruning and reshaping of the neural landscape. The brain employs several distinct and deliberate mechanisms to manage the necessary process of forgetting. One such mechanism is passive fading or decay. This occurs when the neural pathways, the microscopic connections between neurons that encode specific memories, are not sufficiently and repeatedly activated. These pathways weaken over time due to disuse. Another key mechanism is interference, often described as active overwriting, where the input of new and similar information actively disrupts or replaces the older memories already stored. The third crucial process is active dismantling. This involves the intentional regulation of memory strength through the release of specific molecules. For example, a protein designated as P1, PP1 functions as a chemical eraser within the brain, weakening the synaptic connections, the tiny structural bridges that hold a moment's information together. This chemical regulation maintains a functional balance. An excessive amount of the chemical accelerates the fading of essential memories, while insufficient amounts can lead to a mind potentially overwhelmed by the retention of irrelevant detail. Through these precise mechanisms, the mind continuously clears and restructures its internal space, which is essential for ongoing learning, adaptation, and creativity. Forgetting can be a form of mercy. Traumatic memories may be sealed away, their sharp details blurred to protect the individual. Conversely, the frustration of an elusive name is simply the brain prioritizing efficient retrieval pathways. To forget is to grow. To forget is to shed. Children forget much of their earliest years because their minds are still developing the tools necessary to structure time. As we age, while specific details fade, the emotional trace often remains. Memory becomes lighter but no less meaningful. The past cannot be carried in its entirety. We keep what is essential, and the rest falls away like leaves. This is evolution. You are not a storage unit, but a river of continuous change. We have explored the internal rhythms of the heart and mind, but now we turn to the tools of supreme precision clocks, made not of sand or shadow, but of light and atoms. These clocks measure time with an accuracy that vastly exceeds human perception, guiding spacecraft and measuring the minute stretching of space-time. At its core, a clock is a counter that tracks the regular repetition of an event, the swing of a pendulum, the vibration of a quartz crystal, or the energy transition within an atom. The more regular the repeating event, the more precise the clock. In the pursuit of ultimate accuracy, science turned to the tiniest, most consistent rhythm available, the movements inside atoms. In 1967 or 1967, the international community redefined the second. It was no longer based on a fraction of the Earth's unpredictable spin, but on the rhythm of light emitted by a cesium atom. Specifically, 1 second is defined as the duration of 9,192,631,770 cycles of microwave radiation released during a transition between two specific energy levels in the cesium-133 atom. This rhythm is perfectly reliable and consistent. These cesium atomic clocks became the global standard, essential for tasks such as synchronizing global communication networks, coordinating GPS satellite signals, and calibrating scientific experiments. They are so stable that they would drift by just 1 second over approximately 100 million years. However, precision continued to advance. Scientists developed optical clocks, which utilize visible light with frequencies approximately 100,000 times faster than the microwaves used by cesium. Faster oscillations allow for finer measurement and greater stability. The newest optical clocks, using elements like strontium, trap individual atoms in a light-based structure, an optical lattice created by intersecting laser beams. The atoms are then cooled to a temperature near absolute zero, eliminating virtually all vibration. The result is an isolated, pure oscillation, a perfect, silent tick of time. These optical clocks are so sensitive they can detect the time dilation caused by gravity when moved by a vertical distance of just 1 foot. Place one on the floor, and the passage of time is fractionally slower than if you lift it to a table. They are tools that measure not just time, but the very shape of space-time. Their precision is so great that they now measure time more accurately than we can define the unit of distance, the meter. These clocks reveal a profound truth. Time is not just a human concept. It is structurally woven into matter itself. Atoms, completely indifferent to human emotion or memory, still follow an inherent, internal rhythm. While our quantum clocks measure time with objective precision, living creatures experience time subjectively, based on their biology and metabolism. We put aside our watch and explore the differing perceptions of time held by other species. Consider the common fly. It is notoriously difficult to catch because many insects perceive time far more slowly than humans do. Their flicker fusion rate, the speed at which they can distinguish separate flashes of light, is much higher than ours. To a fly, your hand moving to swat, it appears to be moving in slow motion. They live faster, processing more frames per second, making their world appear temporally denser than ours. Now, shift to the other extreme. A massive whale gliding slowly through the dim, deep ocean. Whales breathe in long, deliberate rhythms. Their deep dives can last for over an hour, and their migrations span months. Their biological clocks run differently. Time is stretched for them. When a creature is that large, and its environment is that vast, life is conducted at an unhurried pace. Creatures without the primary sense of sight navigate time using other ancient cues. Sea turtles return to the exact same beaches to nest decades after they were born, guided by the Earth's magnetic fields. Salmon swim thousands of miles upstream, following chemical and current cues. These creatures do not count time. They follow it, carried along by deep, ancient, hormonal, and environmental rhythms older than human memory. Other creatures manage time for sheer survival. Dolphins practice unihemispheric sleep, resting only one half of their brain at a time, allowing the other half to remain conscious for breathing and swimming. Migrating birds can take scattered micronaps while flying. For them, sleep and rest are not single contiguous events. They are threaded and scattered, their perception of hours bending entirely to the demands of movement and survival. Even among humans, the perception of time is flexible. A single year is a vast expanse of novelty for a young child. While it seems to pass in a rush for an older adult, time slows down during moments of intense awe or danger, and it speeds up when the mind is anxious or distracted. There is no single way to feel time, only countless lenses, each shaped by the specific body and mind that wears it. Finally, we turn to one of the Earth's greatest, gentlest timekeepers, the Moon. This silver companion does not tick, but it pulls and guides, marking the months and orchestrating the tides. Approximately every 29½ days, the Moon completes its cycle from new to full and back again. This is the lunar month, the origin of the word we still use today. Before complex calendars, ancient cultures used the Moon's phases to measure and predict patterns of light and darkness. The Moon was a slow, glowing metronome, marking time in predictable, recurring cycles. The Moon's primary function as a clock is through gravity. It pulls gently on the Earth's oceans, creating the tides a silent, constant dance between rock and water. Twice each day, the tides rise and fall, guided by the Moon's gravitational pull. This rhythm has profoundly shaped biological life on Earth. Certain fish, such as the grunion, rely on the tides to reproduce, spawning only during specific high tides. Many corals synchronize their release of eggs and sperm to a single lunar night each year, as if the entire ocean were following a massive internal clock. Even the Moon itself is a massive record of time. Its surface is permanently scarred with craters, each one a frozen moment of impact history. Unlike the Earth, the Moon has no wind, no rain, and no weather to erase these scars. The footprints left by the Apollo astronauts decades ago remain untouched and unmoved. Where there is no air and no life, time leaves its marks differently. But even the Moon is changing. It is slowly drifting away from Earth at a rate of approximately 3.8 centimeters per year. This separation is imperceptible in a human lifetime, but over millions of years, it alters the dance. In the deep past, the Moon was much closer, tides were far stronger, and nights were brighter. In the distant future, the Moon will be too far away to cause the spectacular total solar eclipses that we witness today. Even this constant, ancient rhythm is subject to an eventual, distant end. Yet, tonight, the Moon still glides across the sky, maintaining a rhythm that your body remembers, even if your conscious mind does not. You feel its influence in the rise and fall of your breath, and in the unconscious cycles of wakefulness and rest. The Moon asks nothing of you. It does not rush your schedule. It simply continues, a reliable rhythm you can trust, even when everything else feels uncertain. The capacity of the human mind to mentally traverse time persists even when the body is in physical repose. This ability is known as mental time travel, the neurological function that allows for the retrieval of past events and the construction of future scenarios. This faculty requires both memory and predictive imagination, granting the individual a unique form of existence across multiple temporal dimensions simultaneously. When the brain recalls a specific event, it does not access a static record. Instead, the process involves the reactivation of the original complex neural patterns associated with the experience. This simulation includes sensory inputs, textures, sounds, and the emotional context. Memory retrieval is thus a process of re-simulation, wherein the past experience is rebuilt and accessed as vividly as the cognitive system allows. The physical location of memory in the brain is not a storage drawer. It is an environment actively re-simulated for retrieval. The mind executes the projection of future events with the same fundamental efficiency as recalling the past. Whether planning a conversation, drafting an apology, or rehearsing a potential decision, the brain utilizes the identical neurological structures for future construction as it does for past recollection. The mind operates as a simulator, constantly engaging in prediction, practicing complex responses, and preparing for future outcomes. This predictive function means that a portion of cognitive activity is always directed toward anticipated events. This capability is essential for planning, reflection, and moral reasoning, allowing for conditional statements about past choices and future readiness. The individual's internal timeline, encompassing their past history and their imagined future, is continuously navigated, even in a state of physical stillness. This temporal flexibility, however, introduces psychological complexities. Excessive focus on past events correlates with feelings of regret, grief, and longing. Conversely, excessive future projection often correlates with states of heightened anxiety, pressure, and fear of unpredictability. The mind's ability to travel across time is a powerful computational tool, but it does not inherently guarantee emotional stability. This dynamic emphasizes the practical necessity of presence, the functional act of returning conscious awareness to the current moment for cognitive regulation. The interdependence between these temporal abilities is evident in clinical neurology. Certain forms of brain injury that damage memory also impair the capacity for future imagination. The inability to construct what was correlates with the struggle to construct what could be, confirming that memory serves as the structural foundation for future projection. Even the physiological process of dreams functions as a form of untethered time travel, where the mind processes events, violates chronological sequence, and merges past data with future possibilities. Dreams disregard the external clock and rely on emotional intensity to assign meaning to events across a non-linear timeline. The distinct emotional response, termed nostalgia, is more than simple memory recall. It is an emotional reaching toward a concluded past. While it can produce a bittersweet sensation, its function is often psychologically stabilizing, anchoring the present self by reinforcing its identity through connection to its historical origins. The mind continuously processes its own history through this mechanism. The cognitive system holds the individual, allowing free movement across all temporal directions. When a moment concludes, the question regarding its physical location remains. Though an event fades from sensory input, a residual presence, such as a specific scent or a residual thermal feeling, often persists. We approach the scientific question: does the past remain physically real somewhere in the universe? The foundational principle of general relativity asserts that time is not an abstract moving entity. It is a fixed, physical dimension integrated with the three spatial dimensions. This framework, known as the block universe theory, states that all events from the initial cosmic expansion to the present moment exist equally and permanently within the unified structure of space-time. The universe is described as a permanent, four-dimensional geometric object. The human experience of flow is merely the linear progression of consciousness traversing this fixed structure. Every historical event remains physically present, existing as a fixed coordinate within the block. From this relativistic perspective, the past has not been destroyed. It is located behind the present position of the observer in the temporal coordinate. Physical access to this coordinate is currently impossible, but the past remains woven into the universe's structure. Consciousness functions as a revealing mechanism, moving across the fixed structure like a spotlight. Each moment appears as consciousness arrives, but its existence was permanent within the block. Alternative interpretations, particularly from quantum mechanics, suggest time may be emergent, arising from deeper, timeless physical laws. In these models, past and future may not exist as independent entities, but crystallize only when observed by a system. However, even here, the past leaves verifiable physical traces. Particles maintain memory, and entropy provides an irreversible record of change. The arrow of time is defined by the fixed evidence of completed, irreversible events. Starlight provides the most accessible physical evidence of the past's persistence. Observing the night sky involves viewing light that departed its source years, centuries, or millennia ago. The fact that this light is still arriving, entering the observer's eye, confirms that the effect of the past is enduring. The past is not destroyed. It is simply scattered, held in light, in chemical memory, and in the persistent structure of space-time curvature. The past is not physically retrievable, but its reality is unmade. It has exerted a measurable, permanent influence on the present state of the universe. The knowledge that past experiences the laughter, the learning, the mistakes, remain a fixed component of the universe's structure, provides a functional realization. The past is not eliminated. It is absorbed and carried forward. The journey concludes, having integrated the mechanics of quantum clocks, cosmic structures, and cognitive memory. The individual is not an external observer, but an intrinsic component of this unified temporal narrative. The universe continues to regulate time independently of conscious awareness. The observer rests with the confirmation that the past is permanently written in both physical and cognitive forms. The present moment is physically secure. The future continues to unfold ahead, governed by the established laws of physics and statistical probability.